Welcome to Fundamentals of Artificial Intelligence. Today we will look at the Minimax algorithm and alpha beta pruning. The Minimax algorithm is used to extract the best first move in a game tree. Alpha beta is a layering on top of Minimax that drastically reduces the search space. We will first look at Minimax and see how alpha beta pruning is applied to reduce search space. We are dealing with board games, games such as chess or checkers, or games such as tic-tac-toe, and these games have the following characteristics. One, we are dealing with two-player games, games that have exactly two players. These games are called zero-sum games. Zero-sum games are those in which if one player wins, the other loses the game. That is, the total payoff is zero. One player's gain is other player's loss. The third characteristic of such games is complete information. Both the players are assumed to have access to all information, that is, can see the board and thus know the options the other player has. These games are alternate move games. The player take turns to make their moves. And finally, we consider these games to be deterministic. There is no element of chance in the moves that one can make. We then define a game tree which is used to represent the game. A game tree is a layer tree in which at alternating layer, one or the other player makes the choice. So we have the max layer and the mean layer. So once we have the max layer and then we have the mean layer, and this is how one after another the layers of the tree comes. A game starts at the root with the max layer playing first, and the leaves of the game tree are labeled with outcome of the game. The game ends at the leaf nodes. Now let's look at how one gets to know the first best move in such a board game. It is important to realize at this point of time that for many complex games such as chess, checkers, search to termination is out of question. Like the complete game of chess has approximately 10 to the power 40 nodes. Even a simple game like tic-tac-toe has 350,000 nodes in the complete game tree. Therefore, the question is how we can get to a good first move. The Minimax algorithm that we will discuss today is one that can extract a good move. So this estimate is made by applying a static evaluation function to the leaf nodes, and then the values are backed up level by level. So we have the max parent of a mean node, and then that parent is backed up values equal to the maximum of the evaluation of the nodes. This is because we expect the max player to maximize his gain. The mean parent of the max nodes is assigned the minimum because the mean player is with an idea to get to the minimum of the boards. So let us take a portion of game tree and try to understand the min max procedure. So here is the portion of a game tree, and let us put the evaluations for the leaf nodes. These values 4, 5, 2, 8, these are value of the board from the perspective of the max player. Now, where is the game going, or which of the two choices does this max player make? If you look at the game tree, it's not very obvious at the first look. But if you look it closely and try to see what could Min do best under such a scenario where he knows the value of the leaf nodes, which are actually the max leaf nodes. So if you look at this node of the tree that Min is playing, Min would rather go to the left here than here, because going here would give him a 4, whereas going here would give him a 5, and his idea is to keep the score as low as possible. So he goes there and he backups this node value as 4. Now, going by that same logic, if you look at this other node here, Min has two choices. Either he plays towards this board or he plays towards this board. Playing towards the left would give him the minimum that he is seeking, and therefore he will go to the left, and this node that he will back up is with 2. Now, these are the backup values one level up. Now, having got these backup values, it becomes easier at this level where max is to realize where to go, because max idea is to maximize the total. So he rather goes towards the left and takes up 4, and therefore we have a 4 at the root node. Now, a couple of things to observe in this small game tree, and the way these values have been backed up is in order. Number one, we should just get to the idea of what the min-max algorithm is. What did we do? We went to the bottom of the tree, we computed the static values using some evaluation function, and then backed them up level by level, and at one level we were at the root. At that point we were able to decide where to go. So we extracted the best move. Now, one important concept that needs to be emphasized here is the concept of computing the static values. Static evaluation functions are used to measure the worth of a leaf node, and these measurements are based on features that are thought to influence the worth of that particular node. Like in checkers, it could be the relative piece advantage or who controls the center. In tic-tac-toe, it could be how many ways max or min, as the case may be, can still finish the game. These things then give me some idea of what are these nodes worth, and these values are then backed up. Another thing that needs to be noticed at this point of time is that we have 8 here, which is the maximum value possible, and ideally max would have loved to arrive at that node, but then these was not possible. All he arrived at was the value 4. On the other hand, for min, the minimum value that was possible in this small game tree was 2, whereas he was only able to arrive at 4 and not go below that. Now, this is because these are adversarial games. Min and max are competing against each other, and you do not expect to go where you wanted, because the competitor is always trying to stop you from going there. And that is why we arrived at 4, which was far shorter than 8, and more than 2, what the mean player would have wanted. This min-max search is actually a depth-first search. The min-max search searches the game tree with depth k in a depth-first manner from left to right. So let us try and illustrate this idea. Hope this works and we can see how the depth-first search is done by the min-max procedure. So here is a game tree and all of its leaf nodes are marked. So let us now see how min-max searches the game tree with depth k in a depth-first manner from left to right. So it starts at the max node, comes down one level, which is the level of the mean player. It comes to the max layer, one level down, and finally arrives at the leaf node. Thereafter, it gets the value of the leaf node, which is marked 5 at that point. So that is backed up one level and we get 5 there. Next, this is a depth first search, so it has to go to the mean level, to the leaf node one more time, picks up the value 4, but then when it backs it up, one got to remember that this is a max layer. I am expecting the maximum of the two. 4 is not entered, we still have 5 there because 4 is less than 5. We work with the maximum because this is max. So this is backed one more time up and mean has a 5 there. Now one level down it goes there, comes back to the leaf node and 1 is backed up. So we have a 1 and then it visits 3. Now this is interesting because now we have a leaf node which is more than the value that's at the max level. I have 1 here, whereas now the leaf node value is 3. So it overwrites 1 and keeps the new maximum, which is 3. Backs it up one more level. This is again interesting to note because this is a mean level now and I have 5 there, whereas the backed up value is 3 and mean would prefer 3 rather than 5. So 5 is overwritten and 3 is kept. And finally 3 is backed up to the root of the tree. This is how the left tree is completed. Now to the right subtree, it goes and visits the leaf node, backs up the value 6 and goes and visits the leaf node which is with value 5. So even if it comes back, it does not overwrite because max we are expecting it to have 6 rather than 5. It backs up 6 to the mean and then comes down one final time to the leaf node which is 0, backs up the 0 value. But interesting to note at this point of time that again we have a max node and the leaf value is 8, so 0 would be overwritten by 8. Whereas now when I want to back up 8, I have a 6 and this is a mean node. So between 6 and 8, here 6 is preferred because I am looking for the minimum value of the two values. So finally 6 is backed up and the value of that final root node is 6. So the total backed up value of this game is 6 there. Now we did determine the best move for the max player and these guaranteed somehow that the payoff was maximum for him, regardless of what the move the mean will take. The value of each node is determined by the values of its children, and Max plays the worst case scenario. That is, he assumes when he is doing Minimax is that mean takes moves to maximize his own payoff, that is to minimize the payoff of Max. As already pointed out, it's not possible to expand a game to the end game status. For look ahead, one needs to choose therefore a ply depth that is achievable with reasonable time and resource. Now we need to decide how much depth to we will go when we are searching for the best first move. This is because of the following reason. For a game tree, each node has b children, let's say, and we are doing a d ply look ahead. That means we are trying to go to some level d. That would require that we examine b to the power d leaf nodes. Can we have ways and means of reducing this, because this is a huge search space? So can we somehow reduce this space? Now, search procedures for min-max that we have described up till now separates completely the process of search tree generation and position evaluation. The position evaluation was done only after the tree generation is completed. Separation of tree generation and position evaluation results in grossly inefficient strategy. So is there some way in which tip node evaluation and calculation of backtop values simultaneously with tree generation can be done? If this could be done, we could have remarkable reductions in the amount of search required to discover equally good nodes. So this is exactly what we look for in this layering on Minimax that we are talking of, and that amounts sometimes to many orders of magnitude reduction in the amount of search.